Hi, this is Nicola from NFN Bari, and I'm talking about the FLUKA cross-section for galactic cosmic ray propagation studies. The work has been done with other people, in particular with Pedro, that is online. So, and okay. So, as you know, now, also in this conference, so now we have a lot of nice measurement of cosmic ray near Earth with a very precision level, and this data now are probing, let's say, the propagation models for the galactic cosmic ray. And as you know, right now we have the main, let's say, issue in this propagation model that comes from the knowledge of the secondary production, as you know. In particular, we know that we are using nuclear cross-section to infer the amount of the materials that cosmic ray hitting in the galaxy during, let's say, 10 or 100 million years before to reach our solar system. And so usually we are using the primary, so the secondary to primary ratio in order to constrain the propagation model, because this ratio is mainly due to the cross section. But again, so in order to constrain the propagation of cosmic ray at very high energy, we should let's say know very well what happens at low energy for the nuclei. The current, let's say, way to use this or to calculate the cross sections for nuclei interaction. Now we have some very old data, and the people are trying to fit this few data in order to, let's say, to have a model for the cross section. But there are many other channels that are still missing in the measurement. So. And the people try to mix, let's say, data models that are fitting the data and the model that are by using, let's say, simulation code. In our approach, we decide to just use one single Monte Carlo code that is FLUKA to calculate all the cross section, since this code is using for many years and is well tested against data starting from very low energy up to, let's say, 10 PV or so. And so our approach is just to use one single, let's say, Monte Carlo code. So in this talk, I don't have any time to discuss FLUKA Monte Carlo code. You can find all details in the FLUKA webpage, and you can also find some details in the backup slides. And so once we know this table of cross-section, we can, let's say, test this parameterization by using a propagation code to describe our, let's say, the cosmic ray that hitting the solar system. And for this work, we have decided to use the Dragon 2 code. And again, I have no time to discuss the code, but you can find all the information on the web on this link. Okay, so sorry. You know that the current model to describe the propagation of the galactic cosmic ray is by using a diffuse equation with the loss term. In particular, you can see this is the QE, this source term. Then there is in the red the one that describes the production of the secondary particles, and there are also the diffusion coefficient that enters this equation. I guess that you will know this equation. And this is the way we propagate the cosmic ray in the galaxy. And this is been solved by many codes. So in our case, we use the Dragon 2 codes. Okay, so this is the main item for this talk. In this slide, you can see some, let's say, spallation cross-section as function of the incoming particles energy in JeV per nucleon. And you can see here in blue some data points that are available in the literature. These are the, just for reference, these are the most populated, let's say, tables that we know. And with the color line, we see some models that has been using for this to fit or to, let's say, parameterize this kind of cross section. And we can see that the model, in the best case, agree within 10 or 20%, but there are some cases that so there are a big difference, as in this, or for instance, in this case here. Okay, and another piece of information that we use in the propagation code is the total inelastic cross section that just set the direction length to destroy the particle, the nuclei. So also in this case, the code uses some old, let's say, model that is called CROSEC, and you can see here the link. And in this plot, you can see the comparison between the inelastic cross section calculated with the FLUKA with the solid line and one calculated with the CROSEC with the dashed line. We see that there are some difference between these two models. And again, in this plot, you can see some data. And also in the case of FLUKA, is well, let's say, agree well with the data. And one thing that I would like to point here, for the CROSEC cross section, you can see here that starting from, let's say, 1 TeV, so the model just predict a flat uniform cross section. And we know that this is not true. In fact, in FLUKA, we see that there is against the increasing the cross section. And this is could have an impact when you try to explain the break that we see in the cosmic ray around 3 or so GeV. Okay, so in this slide we can see some comparison of that we have by using FLUKA with the other parameterization with the other with the data. So now FLUKA are shown with this green line, and the gray area just show you the statistical error that we have because we have a limited statistic in the Monte Carlo. As you can see, in all the channels, there is a good agreement. Of course, there are some, let's say, discrepancy, but for these channels, we can say that the discrepancy are at the level of 10% or so. So on these channels, we can see that there is a good agreement. Also, we can see the behavior of the cross section that describe also the, let's say, the resonance to low energy as in the real data. And on this slide, so on this slide, we show just what we call direct or prompt emission production. But as we read earlier in the previous talk, we should take into account not only the hydrogen as target, but also we should also include the decay of let's say short lifetime of the nuclei in the cross section. So in this plot, we can see the comparison between the FLUKA production prediction when we have let's say all the channels that enters in the production as a function of energy, and you can see again that the comparison is still at the level of 10% or more. Okay, so once you have this kind of cross section, you can inject this table in the propagation code. In this case, we use Dragon 2. And the standard way is to just inject the primary spectrum as a broken power law or double broken power law, as you know. And the usual way is to just constrain the propagation parameter by just fitting the boron-carbon ratio. So if you saw that, we get this parameter. So delta is the spectral index of the diffusion coefficient. The 0 over h tell you the diffusion at reference energy. And also in this model, we use half velocity that is around 23 kilometers per second. And in this plot, you can see the comparison between our prediction, the boron spectrum, against the Pamela and the IMS data, also for Voyager data that just show you the spectra before outside the solar system. And this in this plot, you can see all the comparison of the other components.
2 minutes.
Yeah, okay, it's okay, thanks. Okay, so when you perform this kind of work, just fitting the boron-carbon ratio, we check what happens to the other secondary production, for instance, lithium-beryllium. So if you calculate the ratio between lithium-beryllium and beryllium-boron and lithium-boron, we see that, for instance, for lithium-beryllium, we get a very nice agreement, while for the beryllium on boron and lithium boron, we get some offset, but you can see that this shape is well reproduced. So in other words, in order to get rid of this discrepancy, it's enough to, let's say, scaling a little bit the cross-section. In our case, if you, for instance, scale the boron cross-section increasing by 25%, you see that the effect you can go from this line to this one, this level, and also here. And again, so that means that we can have some error due to the knowledge of the cross-section, but this error is not bigger than 10% or more. Of course, you can also constrain the halo size. Again, if you just perform a simulation changing the halo size, and you can, and then you check, as usual, the beryllium production. We are able also to set the halo size, and in this configuration, we get the halo size around 7.5 kiloparsec. It is a value that we already found in the lecture too. So also in this case, we got a nice results. Of course, we can also, let's say, put on the propagation model the constraint of the other secondary production. For instance, you can include not only boron carbon, also boron oxygen, beryllium carbon, and so on. But also, we can also, let's say, constrain the secondary to secondary production, also allowing a small, let's say, scale factor in order to accommodate possible, let's say, uncertainty on the cross-section. And if you did this in the likelihood, we get this kind of agreement. So in this plot, in the slide, we can see what we get by using combining the fit, include also the other secondary production. And this results is achieved by also applying a small scale factor in the cross-section at the level of 5% or 10%. So the message here that if you allow the cross-section to let's say to scale it a bit, we are able to reproduce all the shape of the cosmic rays. And just as a bonus, and this plot you can see the helium-3 over helium-4 that we get. And in this case, we don't use this channel to constrain the propagation model. So again, we got a nice results also in this case. Okay, so I don't have time to discuss all the other channels, but of course, once you have a set propagation model, you know the local, let's say, local interstellar spectra. You can also calculate, let's say, the local gamma ray emissivity. And if you do that, so we got this kind of results, and then you can compare this with the Fermi-Lat data. And again, we got again, a nice result also in this case. So these are my conclusion, and maybe I'm running out of time. So thank you for your attention.
Thank you for your nice talk. Is there a quick question maybe? Online or yes?
Thank you for your presentation. I'd like to ask you which kind of solar modulation you included in your analysis.
Okay. So this is a nice question. So in this case, we are just using the standard FLUKA model. So in order to have a simple setup in our fitting, and the level, so the modulation potential in this case is around 600 MeV. So